Hello everyone and welcome on today's video. My name is Wouter Pere. I'm the founder and main developer of GHEtool Cloud, and today I'm going to talk to you about Sankey diagrams. Now, perhaps some of you already know this type of flow diagrams and you're a little bit excited at the moment. Perhaps some of you do not and you're just a little bit more hesitant or tempered in your feelings. But let me go ahead and explain to you why these diagrams are useful. And then we will go over to GHEtool Cloud, where we've embedded them as a new feature for every calculation you do, in order to gain as much insight as possible in how your system behaves. Now, this is a sketch of a Sankey diagram. So the way you read this diagram is you start at the left. This is basically the input, what goes into your diagram, and you proceed to the right for your outputs. So in this case, you have material, you have packaging coming in, and part of this packaging material is going to be recycled as cardboard. Some of it is plastic, glass, metal, and it will be recycled, but with another process. Part of it is plant-based and it can be composted. And then a final part is going to the landfill. So this is basically a Sankey diagram. It tells you, if you have a certain input, how it proceeds to the output, of what output streams are there. And what is important is that the input in a Sankey diagram is always equal to the output. There is no material lost in this case. Now here you have also the reuse stream. This is a little bit controversial when talking about Sankey diagrams, whether or not there are loops, but we will not go into that. But this is for material. You can also have it in economics. So this is, for example, the way you spend your income salary. So you have your gross income, part of it goes away to taxes. Then you have your net income, and that you can spend also on different categories. It can be visualized like this. You can also do it for more complicated energy systems. So this is, for example, a flow chart of the energy consumption in the US with the different sources of energy and how they are used residentially, industrial, transportation, etc. So it's very powerful to visualize complicated things, and it can become really complicated. This is, for example, for the greenhouse gas footprint with all the different sources and where they're produced, etc. So these type of Sankey diagrams are really insightful in order to visualize how your energy, how your materials, how your emissions flow through a whole system. And up until now, there was no possibility somewhere to do the same thing for geothermal energy, shallow geothermal borefields. And that's why we've embedded Sankey diagrams by default now in GHEtool Cloud, so that it's also an output or a result for every simulation you do. So let's go ahead to GHEtool Cloud and talk about Sankey diagrams for geothermal engineering. So I created a new project in GHEtool with a couple of different scenarios to show you how you can use these Sankey diagrams to interpret your results. So we'll be talking about our general simulations, let's say, then a case with active and passive cooling, a hybrid case, and even active, passive, and hybridization. So I just use the default values here, and if we go to the results tab, and this is typically what you're familiar with, your numerical results, your temperature profile. But now we also have here the Sankey diagram. So the way you should read this, again, is from the left to the right. But as you can see, there are 4 different colors used on this graph. So we have all the reddish orange colors, and this has to do with the heating, the hot side of your system. Let's say it's the heating demand, it's domestic hot water demand, and your ground source heat pump. This is all red. Then you have your blue colors. This is everything which has to do with cooling, with the colder part of your system, your cooling, your passive cooling, your active cooling as well. Then you have 2 purple streams. This is what you can see as the inputs, which is inputted into your system in order to make sure your geothermal system can deliver your heating and cooling comfort. So this is the electricity that you need in order for your function to operate, and also the imbalance. I will go into that a little bit more detail in a minute. And then you have your green part as well, which is the STES. It's short for Seasonal Thermal Energy Storage. Now, if you think about shallow geothermal bore fields, you see them as a way to store energy and not so much as a source of energy. Now, deep geothermal energy is typically seen as a source of heat, whereas shallow geothermal energy, you have typically both heating and cooling. So what you do is when you cool your building, you store that heat into the ground where it can be used in winter to heat up your building again. And that's actually the main advantage of a geothermal system, a shallow geothermal system, is this storage, this seasonal thermal energy storage. And ideally, you don't have any imbalance and your ground stays the same year after year after year in temperature. But oftentimes, this is not exactly the case. You always or almost always have an imbalance. And this imbalance is actually using the ground as a source of heat. So you're going to cool down or heat up the ground year after year. So you're using a little bit of this energy as a source. And that's actually what you can see in this graph. So if we start here, we have our cooling demands, 7,600 kilowatt hours of cooling. And this cooling is 100% delivered, in this case, with our passive cooling. Now, as you can see, our passive cooling, it takes the cooling demand for our building, and it also takes a little bit of electricity. And because there is a primary pump running to keep the flow through the bore field going, it consumes a little bit of electricity. And together, the energy from our building, the heat coming from a building, and the electricity, this will be stored in the ground, in our seasonal thermal energy storage. Now, in total, 8,022 kilowatt hours are stored in a bore field, and this is given to our ground source heat pump. Now, our ground source heat pump uses, of course, a little bit of electricity, almost 4,700 kilowatt hours. We typically want this to be as low as possible because the electricity it's expensive, it's an operational expense, so we want a high efficient heat pump with as low electricity as possible. Then we have the energy which was stored through our passive cooling, and then we have here the imbalance. Actually, what we use, where we use the ground as a source. And then this ground source heat pump, part of it goes to the heating demand and part of it goes to the cooling demand. So this is a really interesting way to visualize your system because you can, for example, go on the electricity node and you see, well, of course, most of the electricity here is going to the ground source heat pump. Now, if we say this is for a negative imbalance, where the ground cools down year after year, if we have a positive imbalance, where the ground cools up, the story is a little bit different. So here we again have a cooling demand. The cooling again goes to our passive cooling, which consumes a little bit of electricity. And here, because the imbalance is the way around, we are putting more heat into the ground than we are using for heating our building. So part of the passive cooling goes to the seasonal thermal energy storage to store this into the ground. And part of it is imbalance. Now this imbalance is again the same as you can see here. It's geothermal imbalance. It heats up the ground year after year. And we want this to be as small as possible, as said before. And the seasonal thermal energy storage goes to the heat pump. This heat pump consumes a little bit of electricity, and this goes towards our heating and domestic hot water demand. So it's the same reasoning, but now the imbalance is not a source, but it's more a dump. It's dumped into the ground. And ideally, you want your system to be almost balanced. So where you can see that, if I jump back, here the imbalance was 8,000 kilowatt hours. Here it's smaller with 2,800. So you want typically your seasonal thermal energy storage to be as large as possible, because then you will have the best efficiency of your geothermal system. Now this is a diagram you will see for most of your calculations. Now if you go towards the active and passive option, here the situation is a little bit more complicated. So we have all our graphs here. So the way you read this diagram is again from the left to the right. So now you have your cooling, but part of your cooling is done passively and part of it is done actively. Now for your passive cooling, again, part of it is stored in the seasonal thermal energy storage. Part of it is going to the imbalance. And for active cooling, it's the same. Part of it is going to the storage, part of it is going to the imbalance. The storage, both with passive and active cooling, goes to the ground source heat pump. And since there is a negative or a positive imbalance, it only is the storage going to the heat pump, and the heat pump powers the heating and domestic hot water with a little bit 36 megawatt hours per year of imbalance. Your hybrid system, it's also something you can do where you hybridize your system. So here you see that we have 8% of heating from a hybrid system and 17% of cooling. The Sankey diagram then looks like this. So now you have our cooling. Part of it is passive. Part of it is delivered by your hybrid system. Then this cooling goes again to the seasonal thermal energy storage and to the ground. And then part of your heating is now not only coming from the ground source heat pump, but also from your hybrid system. So this is yet another way to visualize how the energy flow through a hybrid system, how it works, what's the part of the ground source heat pump here. You can see that it is way bigger than the hybrid system, and the same in cooling. So this is again another way to visualize it and to interpret your results. Yeah, and then finally we have the most complicated graph you can create. It's with active, passive, and a hybrid system. And then it looks, for example, like this, where you now have, in the situation we calculated, a way bigger share of our hybrid system for heating. And our cooling demand is now spread over active cooling, passive cooling, and our hybrid system. And both the active and passive cooling go to the seasonal thermal energy storage, and this feeds into the ground source heat pump, where it also takes the electricity and just a little bit in balance actually. So it's 80 megawatt hours in comparison to 263 megawatt hours. So I hope you found, or you think this diagram is also interesting for you. Please interpret it, play around with it. It's not yet included into the report, because in summer we're going to do a total remake of the report, and then it will be included, so stay tuned for that. But I hope by making this default for all of you, that you can learn how your system behaves and that you can start building better geothermal systems with GHEtool today. Consider subscribing to this channel, sharing this video with your colleagues, and I see you next week. Take care. Bye.